then you are not able to close the superconducting gap. And this is summarized here. You see that as a function for very low fluence, pretty much this is close to 1. So you are sending energy to the system, you are barely affecting the superconducting gap. But as you increase the fluence, eventually you can completely close the gap. This regime is very interesting to understand only superconducting state properties. When we do experiment in equilibrium, what we are finding today is we are actually kind of getting an average of these two things. So this is very powerful because we can now really select what we want to look at and extract all the information we can. So going back to, I can skip on this. One thing, and then I'll go back to the original theme, but I think this is just interesting to show. Here, pretty much now I'm showing you this gap dynamic if you are on the Fermi arc. And so this one is very close to the nodal direction. You can see that the Fermi gap is very small, the gap is very small. And this is outside the Fermi arc. So these are equilibrium spectra. Everything is divided by the Fermi function. And these spectra here are all transient spectra, so non-equilibrium spectra. So you clearly see a very big difference here. So here I'm using the maximum fluence that we use. So this is 10 microjoule. And you can see here that when you are using, when you are sitting at any point on the Fermi arc, at those high fluence, you completely close the superconducting gap. But what you see here is that when you are sitting outside the Fermi arc, and this is true, we studied 3 angles outside the Fermi arc in the original experiment because we were limited by the probe of the laser. Now we have a new system that can do the experiment at 22 eV, so now actually we are studying this regime here. This for next time, next conference. So here the interesting thing that you see is that when you are sitting here, and this is true anywhere here, I can tell you now that it's true also here, although now we see some new state coming in when we do this part. What you see is that there is some suppression of spectral weight, then eventually start to go back to our equilibrium. So you gain back the intensity, which is the spectral weight. But you see it's like if you are creating something inside the gap. So if you think about the typical BCS model, you have a gap, like 2 peak and gap. What is happening as a function of time here, you are filling in the gap. While here, the 2 peak are coming close, you are closing the gap. So this is telling you that there are 2 different dynamics going on. And so if we look now, we do the same exercise we did before. So we are looking at this gap minimum. Now what I'm doing, I'm again zooming in close to t equals 0. And so when we zoom in close to t equals 0, what we see something similar, that the gap doesn't respond right away, but there is a delay in the response of the gap. And this is true at any fluence we used, up to a certain point, which I'm going to show you in a moment. So this is telling me that I come in with up to like 15 microjoule, and 50 microjoule actually is the point where my fluence curve will go to 0. So I'm completely closing the gap. But if actually I look at the moment at t equals 0, my gap is just starts to respond, doesn't respond right away. And if I do this experiment for a conventional superconductor, I do this within the fluence I can access, so 4 microjoule, this is the minimum I can go, the response is almost immediate. Although now there are some optical experiments where you can do lower influence, and they show that if you can go lower influence, they actually see something very similar. So there is something that happens in this regime which seems to be, obviously it's not an immediate response of the system. And so here is the interesting thing. So what we can do the experiment in the superconducting state. And these are, again, zoom-in data. And here we're looking at the intensity. So I go back to look at the intensity. And you see that there is this delay in the response, which is not what was predicted or measured or learned before with optical experiment. There is this delay here. And this is what we call now a build-up time. And then what is very interesting, you see, same experiment, same everything, but if you are measuring now, so this is in the superconducting state. This curve is here also in the superconducting state, but it's for energy bigger than the gap. So one advantage that photoemission has, I have selectivity in momentum, and I have selectivity in energy. So I can sit at the Fermi level, I can sit inside the gap, I can sit at a state well down in energy where the gap is closed. And I can study the dynamics. So I can really have this selectivity in energy and selectivity in momentum. So you see that if I am what I call the superconducting state, means if I'm sampling energy inside the superconducting gap, then there is a delay in the response. But if I measure an energy that is past the superconducting gap, then the response is almost immediate. You see that the peak goes closer to 0. And then finally, if I do the same experiment in the normal state, then you see that the response is also quite fast. So you have a maximum right away, which is what in a simple, thinking about a simple picture, that's what you would expect. Come in, excite the system, boom, response is immediate. So there is something particular about superconducting state, in particular when you are inside the gap. So then the next thing you can do, you can say, well, what if I sit in that particular point? So I am in a superconducting state where I have a gap, I'm sitting inside the gap, I do my experiment, but now what I'm changing the fluence. So I'm changing the amount of energy I'm delivering to the system. Okay? So, and I show you before that depending how much energy you give to the system, you can not affect the gap at all, close partially the gap, completely close the gap. So this is summarized here. You see that if you are in a regime where the gap is affected by a tiny bit, but you are still closing here, you are closing the gap by like 60%, then you see that there is a delay in the response. So the system doesn't respond right away. But if you go to a fluence where I pretty much killed everything right away, at this fluence, then the response is immediate. So what we learn from here, and then we can do this and we can compare with what we learned from the superconducting gap, and we saw that every time the energy I'm delivering to the system is big enough to kill all Cooper pairs, this is what is happening here, then my system responds right away, as we are observing in many metal we are studying. The response is right away, immediate. As Stefano talked about topological insulator, we have several papers on that. The response is immediate. You do this, you have immediate response, although if you have your sample prepared in a certain way, you see that this peak can finish all the way up. And this is because of Fano and some other dynamics. But, so going back here, then we are learning this effect. So then we can do the same thing in the normal state. And again, this is what I told you before. There is no build-up time, response is immediate, no matter how much energy you are delivering to the system. So we can do the same thing, and I think this is very interesting, and I don't think we have a full explanation for this, and we have some idea. But what happens is the following. So what I'm doing now the experiment as a function of momentum. Here, just summarizing few data. So you see that if I'm here at the node, away from the node, all the way up to this point, there is always a delay in the response. Okay, so far I led you to think that this delay is related to the superconducting gap, which actually is. Okay, and so you are here, you come in, the system responds. It takes some time before response. Every single thing we looked at takes time to respond. This is true as I move on the Fermi arc. Now you would expect that if you go away from the Fermi arc, where we know that the gap is really big, we have these two gaps. We have one gap and another gap outside the Fermi arc, which is much bigger. But when I sit here, and it's the same any point here, now we can go all the way up here, any one of these points, I do this experiment, the response is immediate. So I have a very big gap there, and my system responds right away. Anytime I'm sitting here, I see a delay. So this build-up time is obviously related with the superconducting gap, because I show you that if I do add energy above, there is no delay time. If I completely kill all the superconducting pair, there is no build-up time. I show all this. The only patterning point is this. So what we think out of this, this is for other sample, we see the same thing for all different doping. There is some doping independence of this build-up time, but this is beyond. So what we think is going on here is that the way we can explain this build-up time at t equals 0, this is a very complicated slide. So this is some prediction from my colleague Dunhaiti. So the idea is that whenever you have a system, and forget about the slide, it's so complicated, but whenever you have a system, you are in the superconducting state, you are coming in with the light, you are breaking partially Cooper pairs. Okay? So the energy of the system is stored in the lattice degrees of freedom. So this is where this energy is going. And so the idea behind it is what he called the equivalent of a stimulated emission process, which is the fact that for the non-equilibrium quasi-particle, if you are in this low fluence regime, which means you still have a lot of Cooper pairs, but you are partially breaking Cooper pairs. In this regime, there is a much higher probability that this energy stored from LAT goes back to recombined pairs, and this phenomenon is like a stimulated emission process. If you are in this other regime, where the fluence is much bigger than the critical fluence, you pretty much have killed all the Cooper pairs, and then this type of recombination process doesn't take place. And so, this in a way goes back to, there's been some paper that I was not aware of, that I've been reading, saying that one of the explanations of the zero in the resistivity and why impurity don't kill the resistivity, the zero resistivity in a superconductor, is because of stimulated emission. So there is a much higher probability for quasi-particle Cooper pair come in, they break because of an impurity, and the probability to recombine is much higher because of this stimulated emission. If this is the explanation or not, I don't know. It's a possible explanation, and I always invite someone else to come up. So they did some simulation, and they showed that actually if you add up now this stimulated emission process, this is a delay. So it's like in a laser, pretty much. It's the same type of phenomena. So, last thing, and then I let you go. So, one interesting thing is that I told you at the beginning that everything seems to respond within this energy scale, which is the phonon energy scale. And these are different spectra, so they look a little bit noisier. But the interesting thing is that when you look at the phonon energy scale, you have exactly the same phenomena. Pretty much at t equals 0, here I'm showing the difference between equilibrium and normal state. Between equilibrium and transient state. So you see here that the difference is almost 0. Meaning that even if I came in with a pump, the non-equilibrium state I created is almost the same as the equilibrium, which is telling you that it's like if there would be a delay. And when you go down here, now you see that there is a big difference. And so, in conclusion, pretty much, we can look at the time scale associated with the electron-phonon coupling, and we see the same thing. We see that the electron-phonon coupling is a kink if we are in that energy region between 0 and 150 femtosecond, where the gap doesn't respond, and the system has this delay, then even the electron-phonon coupling doesn't respond. The moment we pass that, then the electron-phonon coupling respond very closely to the superconducting gap. And this is just a summary of the thing, and this is really, where we are going in the future. And next time probably we'll start to talk about the new regime that we can create now, coming in with mid-infrared and terahertz pumping for our system. Thank you for your attention.
Thank you very much. We have time just for one question.
One question. Actually, Alessandra, if you have a gapped system and the gap is delta, in order to
start to change it. Alessandra, you can come.
In order to destroy in time this system, you need a time 1 over gap, 1 over delta. If you have gapped the system, the delta is the gap. In order to destroy in time the system, you need more or less a time 1 over the gap. So this means that in the superconducting state you are a delay in destroying the superconductivity. In the Fermi liquid normal system you have no delay. So probably this is I don't understand exactly which is the gap, but you can estimate.
Yes, but if
time.
this was the case, then when I am in a region where the gap is big, then the effect should be much bigger. I should have a much bigger delay.
Yeah.
And instead I
Well,
show
he's saying
you.
1 over delta.
What's
1 over delta.
He's saying 1 over delta.
Yes, but again, 1 over delta, but you go from Fermi arc to outside the Fermi arc. Okay, you know how the D-wave gap goes. So the change of the gap is not enough to justify that you go from a delay time that is, now I don't remember how much it is, but it's relatively big.
A few picoseconds.
To a few picoseconds, I don't remember the exact number, to a gap that changed by 2 millielectron volts.
Which is the value of the gap, more or less?
The gap, well, it's momentum dependence. I can go, if I'm on the Fermi arc tip for this doping I was showing, but it's obviously doping dependence, it's like 15 millielectron volts, and when I go to the next angle, I can do it, it's like 17 millielectron volts. I have 2 millielectron volt change of gap, which doesn't justify the effect to be completely gone. and I move inside the Fermi arc where I go from 1 milliV gap to 15 milliV gap, and the build-up time pretty much doesn't change. So this 1 over gap scenario would tell me that if I am near the node, I would have a certain build-up time, and then as I go, I move away, the build-up time would decrease, which is not exactly what I see. Within the error bar here, it's always the same. And then I go from this point away by 2 millielectron volt, and it's completely gone. And then the effect is very much doping dependent. I show you the doping dependence. They actually scale opposite to 1 over delta. Because then you would imagine you go for an underdoped sample, and then and you compare it with an overdoped sample. You have a big gap versus a small gap, and actually you see the opposite thing. And where we see the biggest effect of the build time actually is at optimal doping, where the gap is somewhere maximum. So it's not exactly, there is something else going on that's important.
Okay,
Thank you.
Thank you very much. I think